All right, let's do a couple examples where you have to find the actual length of the curve using our new formula. So here are the actual questions. Why don't you actually pause the video, try these out yourself, and then I'll do them with you. Okay, so hit pause, give these a shot based on the last video, the formula, and we'll see how you do. All right, so the first one, let's see here. Let me just copy down super quick. We had y equals 2/3 x to the 3/2 plus 1 from 0 to 1. There we go. Okay, from 0 to 1. All right, so then the arc length is going to be the integral from 0 to 1, square root. It's going to be f prime of x squared. So I need f prime of x. So f prime of x is, let's see, that's going to be x to the 1/2. And I think that's it, right? Because plus 1 is just 0. So this is my f prime. So then my f prime squared is going to be x to the 1/2 squared plus 1 dx. Okay, and remember, all this is doing is the distance formula. That's all this is, the distance formula. And you're adding up a whole bunch of them, right? An infinite number of them. You're adding up all these little distance formulas. So the little segments on the curve are being added up to represent the actual length of the curve. So this actually, I think this one we just do by hand. This becomes x to the 1/2 is obviously just x plus 1. A little reverse power rule. Reverse chain rule kicker doesn't really come into play here because the derivative of this would have just been 1. So this becomes, that's x to the 1/2. So it's going to be 2/3 x plus 1 to the 3/2 evaluated between 0 and 1. Okay, so you could do the x plus 1 to the 1/2, do your reverse power rule. There's no reverse chain rule kicker, and I think we're in good shape. So this becomes 2/3 times 2 to the 3/2 minus 2/3 times 1 to the 3/2. So it's just this. So I guess we could simplify this in radical form, but at this point, I don't think there's a need. We could just put in the calculator and get what we get. Let's see. 2/3 2 to the 3/2 minus 2/3. I get 1.219, I guess. 3 decimal places. Okay, so there's your arc length formula with an example. All right, let's try the other one. Let me pull that back up. That one is a little tricky. So 0 to, actually, sorry. Y equals sine x from 0 to pi. Switch screens. So 0 to pi, square root. Derivative of sine, of course, is cosine, so it's going to be cosine squared plus 1 dx. I'm not doing that one by hand, so this one we're going to go straight to the calculator and get what we get. So this is going to be, there's a little glare there. Let's see if I can find a better spot. There we go. How about that? Make sure you're in radians, of course. So we're going to do the square root. Cosine squared, so I'm going to put that in parentheses, cosine x squared plus 1. Close the parentheses for the square root, comma x, comma 0, comma 1. Close the parentheses for the whole thing. Easy way to check is, do I have as many lefts as I do rights? 1 left, 2 left, 3 left, 4 left, 1 right, 2 right, 3 right, 4 right. So at least I have a pretty good shot at this not coming back with some kind of error. And see what we get. I got 1.311. Okay. And that doesn't look right because for some reason I did 0 to 1, which of course was the last example. And I believe this one said 0 to pi. So let's try doing it the right way and see what we get this time. How about 3.820? Is that what you got? Okay, I heard you. Just making sure you're paying attention. Okay, so the cool thing is once you have the formula, it's pretty easy to do. All you really need is the derivative to be able to put in the right spot. But the concept was, if you go back to the other video just to double check, the concept was simply finding a whole bunch of distance formulas and adding them all up. It's not that much different than when we did area or volume. So the whole idea, this whole integral concept gets us an infinite number of things that we can add up. Right? Think of sigma notation. Okay? So there is your basics. Let's do an AP style one. Okay, I don't think I showed you that one yet. That's this one. And yeah, there we go. So hit pause, try that one out, see what you get, and then I'll do it with you. All right, let's see. So they're giving you the length of the curve, right? Let me just copy this down super quick. 1 plus 9x to the fourth dx. Switch over. All right, so they're giving you this. And they're asking you something about the original function, the actual curve itself. So if you look at this and you interpret it, you know there's your limits, right? The square root of 1 plus this. Okay, so they wrote it in a different order, but it's the same idea. This right here, if you think about the formula, represents f prime of x squared, right? Isn't that the formula? So 1 plus f prime of x squared. So 9x to the fourth is f prime of x squared. So that means f prime of x must have been 3x squared to begin with. And if that's f prime of x, then f of x had to have been x cubed. Ah, good, you said it. I wasn't sure if you were going to say it. Good job, I heard you. Plus c. All right, and then I think they give us some kind of initial condition, right? The point has to contain 1, 6. All right, well, that's how we get our c. So 1, 6, so 6, 1 plus c. So c equals 5. So f of x must have been x cubed plus 5, which, if we go back to our choices, was b, which is correct. That could have been the equation for the curve. Okay? All right, I think that should be good to get you going. If you need any help, of course, let me know, and I will talk to you guys later.